Somewhere, something incredible is waiting to be known. This popular quote from Carl Sagan challenges us to imagine the possibilities of discovery, whether far away into the night sky or even here under our feet. And certainly when we look at a beautiful night sky, there are some incredible scientific questions that we can ask ourselves. What would life be like if we lived in a different atmosphere? What pressures are the stars experiencing, and how is this affecting the chemical reactions occurring thousands of miles away? Scientists want to answer these questions. We hope to probe into how we are made and to think about answering why we are here. And certainly, as you can imagine, these otherworldly questions can be quite difficult to answer. For instance, our nearest neighbor planets illustrate a drastically different atmospheric pressure than what we experience here on Earth. You can also consider the chemical differences of reactions that take place below our feet. When we especially consider the geological pressures that can be achieved, it becomes almost an impossible task to think about how we can experimentally simulate these pressures within a laboratory setting. How is it even possible to simulate something that is, for instance, 364 gigapascals in pressure? How is that even physically possible for us to do in the laboratory setting? The answer to this question came with Percy Bridgman, who, in the early 1900s, won the Nobel Prize in Physics for accomplishing such untold feats of high pressures in the laboratory setting. His method is coined the diamond anvil cell, which, at the time, enabled syntheses of up to 10 gigapascals in pressure. The diamond anvil cell utilizes two opposed ultra-hard diamonds to be adhered within a steel piston cylinder apparatus. The diamonds can withstand immense pressures and are optically transparent to allow for numerous analyses under pressure, including vibrational spectroscopies, diffraction scatterings, optical sample viewing, and accurate pressure measurements to a known standard, such as Ruby. Today, diamond anvil cells can reach maximum pressures of 400 plus GPa, but come at an extreme cost, hardly any sample. The extreme pressures enabled by diamond anvil cells are not achieved by a mechanism to increase the force press on the material, but rather to decrease the area upon which the material is present. The area of the diamond tips, called culettes, are often 400 microns or less in diameter, with reaction chambers often 100 microns or less in diameter. This small area results in very small sample sizes of nanograms of material or less, which is very infeasible for larger industrial practices and synthetic material mass production. The Paris-Edinburgh press, or PE press, exhibits a much larger volume to enable milligrams of sample material to be synthesized at the cost of a major pressure reduction. For the Center of Nanothread Chemistry, this press continues to manufacture within a range necessary to synthesize our desired material, nanothreads, as the maximum pressure is about 20 GPa. PE presses, similar to diamond anvil cells, have two opposing anvils that are made of polycrystalline diamond rather than large diamond crystals. Our V7 press anvils do not have the capability to perform in situ spectroscopies under pressure, but anvils can be accommodated or can utilize high flux synchrotron radiation to study reactions under pressure. We can similarly continue to decrease the capabilities of our pressure apparatus, but increase the volume output to tens of milligrams in the case of a multi-anvil press. Multi-anvil presses, such as the one here from 13IDD at the Advanced Photon Source at Argonne National Lab, can vary drastically in size depending on their use in material product formation. Recent advances has enabled some to reach sizes of 10 by 15 feet to accommodate pressures of up to 20 gigapascals if necessary. The focus of this video will be on the PE press and how we operate it at the CNC on a daily basis for material synthesis. Here are the schematics of our PE press at Penn State. To generate pressures up to 20 GPa, a syringe pump is utilized. A syringe pump has the capabilities to flow a set volume of oil into the PE press. The press is held up by blue supports to enable tubing from the syringe pump to admit oil into the press. The bottom half of the press encompasses the piston. As the piston fills up with oil set by a command in the syringe pump, it will slowly raise in height. This movement generates a huge amount of force as two opposed anvils are sandwiched tightly together containing the sample. The close contact of the anvils is achieved by a threaded screw as seen on the upper piston. Our V7 press can reach up to 450 ton of force generated from a 66 milliliter syringe pump to enable pressures of up to 20 GPa on a small encapsulated sample. The anvils are one of the most important and unfortunately breakable pieces of the PE press. Our anvils at Penn State have a slightly optimized design for our work, and we illustrate a unique capability to synthesize our own anvils at Penn State. The inner polycrystalline diamond can be manually machined using an electric discharge machine to achieve a curved surface profile as illustrated here. The polycrystalline diamond is then adhered in an outer diameter of tungsten carbide and a steel jacket. The radial pressures between the jacket and the diamond are about 0.5 GPa and are pressed together with a standard laboratory press. A gasket after compression is illustrated next to the polycrystalline diamond anvil to the right, which is used to encapsulate a material during compression. The inner bump highlighted represents the reaction chamber, with the double toroid rings enabling the reaction chamber to remain gripped to the polycrystalline anvil. We would like to acknowledge all of the help we have received in being able to machine these anvils at Penn State. We thank Ellis Dunkelbarger and Ronald Weaver from the Penn State Engineering Machine Shop for the help in machining the anvils, in addition to Malcolm Guthrie, Stefan Klotz, and Jamie Meliason for their advice and guidance. We established before that diamond anvil cells use an internal pressure calibrant conjoined with fluorescence to monitor the pressure of the reaction. Yet for a PE press, we have no optical window to assess an internal pressure calibrant as we have polycrystalline anvils. So how do we know what pressure we are at? For the PE press, we simply relate our desired force to the oil pressure we are inputting from our syringe pump. We can work backwards from the desired pressure in gigapascals to an established equation from the Edinburgh group to calculate the amount of force needed to be generated in tons. From this force, we can use a known standard oil pressure acquired from our previous lab mates at Oak Ridge National Lab, which can finally be converted into the oil pressure necessary for us to use our PE press, which is the V7 PE press. In total, we measure the output of the oil pressure from the syringe pump into the piston of the PE press. For our experiments, this may look like the following example, and should we decide various pressures, rates at which the syringe pump will input volumes of oil, and hold times after reaching a specific oil pressure. Oil pressure does not translate into something intuitively, but we are simply relating an input of force to our desired GPa of pressure to achieve a synthetic formula as desired. Experimentally, how do we load a PE press? In short, we place a specified volume of a solid or liquid into a stainless steel gasket which encapsulates the material. The gasket serves to prevent the precursor material from being compressed into the polycrystalline diamond anvils, which could crack or break the anvils. Our PE press at Penn State is a V7 press with double toroid anvils, equivocating to a volume of 16.8 millimeters cubed. A double toroid means that our sample will be shaped similar to a sphere in geometry. As a result, our gasket material is composed of two cups, one of which our material is placed, and the second of which is placed above our material. Two rings of stainless steel are also present and placed adjacent to our material to act as grips when the steel gasket is pressurized. These rings help prevent blowouts and duly prevent the material from seeping out of the press when compressed. For clarity, I am illustrating the cups as green spheres and the rings as blue and black circles for simplification in the upcoming diagrams. When the gasket is compressed in the PE press, the rings and cups completely encapsulate the sample. Such extreme pressures are achieved to mold the rings and cups together into one entity as shown on the right. But before we compress, you might be wondering how exactly we load our precursors, especially when the geometry is a sphere and we have a liquid sample. To load a liquid sample in the PE press, we should be aware that our gasket is round. As air is more compressible than our liquid sample, an excessive air while loading will risk enabling the gasket to collapse in, potentially affecting poor yield. To thus maximize the amount of liquid sample held in the gasket, we must freeze the liquid first to fit the exact contour of the gasket cups. We will do this by assembling a liquid nitrogen bath within a styrofoam container. The anvil can be supported above the liquid nitrogen bath with a metal support. We typically use a metal laboratory scupula. This is important as the metal support enables easy removal of the anvil from the liquid nitrogen after freezing our precursor. Recall that our sample is encapsulated within a stainless steel gasket. With our current anvil design, this is composed of two cups, an inner ring, and an outer ring. These must also be cooled within the liquid nitrogen atmosphere to avoid melting the frozen solid after transfer to the PE press. We will be using one of the cups to freeze our liquid into. After cooling the gasket pieces for 10 to 15 minutes, we are now prepared to freeze our liquid precursor. Using a syringe, we can obtain 23 microliters of the liquid chemical, illustrated here in purple. The objective is to drop a single 23 microliter droplet onto a cold gasket cup. This step is crucial to obtaining a round solid that matches the contour of the gasket. Some tips for obtaining a nice droplet include remembering that liquid nitrogen fumes can freeze the droplet within the syringe. Be aware that you must move quickly. Due to the fast freezing process, it is easiest to drop about half a centimeter above the gasket. Remember, we want a single round droplet. A droplet that looks like 2 scoops of ice cream does not match our gasket contour and can potentially risk an excess of air in our reaction chamber. One fluid, quick motion with the syringe release can help mitigate your chances of receiving 2 scoops of ice cream. Finally, remember that you can always load multiple times, so don't be frustrated. Look at your droplet after it is cooled to ensure it is the size and shape appropriate for compression. After the droplet has cooled, the gasket pieces can be moved to the center of the anvil, with the second cup being placed on top of your sample. When you are confident to move the anvil to the PE press, you can do so using a pair of pliers. Remember to use appropriate PPE, such as gloves and a face shield, as the anvil will be very cold and not safe to touch. The final step is to push the anvil into the aluminum cylinder. It helps you keep a gloved hand ready to assist. Remember to check the gasket pieces to ensure they remain in the center of the anvil. Slight offsets of the gasket could result in a blowout, where the gasket pieces shoot out of the press due to an unevenly distributed pressure. Screw in the top anvil so it is in contact with the sample gasket. Use the giant wrench and your body weight to ensure appropriate contact. At Penn State, we have 2 shields to place over the PE press to protect passing scientists in the unlikely chance of a blowout. Be sure to add these shields before any oil pressure is applied to the press. Once the shielding has been added, open the pre-pressurized oil valve that connects to the syringe pump. This will seal in the gasket pieces and also ensure solidification of the liquid using pressure in addition to the cool environment. A typical good seal will be generated at 115 bar from our syringe pump, which corresponds to about 3 GPa of pressure. This amount of pressure will solidify most liquid organics. At this point, the press is loaded and ready to run. At Penn State, we have a home program command line coded in Igor Pro. Target pressures can be input into the Igor Pro command line, and the syringe pump will input the oil necessary to achieve the pressures desired. The compression of solids is arguably much simpler, especially if the material is soft enough that it can easily be powderized. Traditionally, pellets are easier to obtain from better powders, as it enables the material to hold its shape after compression. Powder samples can be achieved by grinding with a mortar and pestle, or by using a grinding mill if necessary for harder inorganic materials. Softer organics can often melt during the grinding process, which is key to avoid recrystallization. An ice bath or liquid nitrogen bath can be utilized depending on the melting nature of the material to avoid the conundrum of recrystallization. After a powder sample has been formed, the powder can be scooped into a pellet press, as shown on the diagram to the left. Our pellet press at Penn State was manufactured to our gasket cup geometries in order to form a small ball of material that matches the geometry of our anvils precisely. A measured mass of sample can be loaded into the pellet press, and the pistons will compress the pellet against a lower support to about 1 ton of pressure using a hydraulic press. There is a calculator available from the Snap Beamlines at Oak Ridge National Lab, in which the bulk modulus and density of the powder can be used to calculate the sample mass needed for a specific encapsulation. For the V7 press at Penn State, this volume is 16.8 millimeters cubed for double toroid anvils. This calculation helps to account for changes in compressibility of the material to avoid snapping the geometrically designed pistons. In the case of an unknown or newly synthesized material, it is always recommended to err on the side of caution and add more material than necessary to avoid snapping the pistons. Powders can greatly vary in density and bulk modulus and may not behave as anticipated under pressure. Generally, for organic powders, an estimation material needed can be gauged from the density from a known crystal structure and the volume of the gasket encapsulation. Adding 2 to 3 milligrams for the safety of the pistons is ideal. After obtaining the ball of solid, it can be placed within the gasket material on the lower anvil and compressed at the desired rates and pressures specified by our homemade Igor Pro program. Shown here is a sample of benzoic acid that was compressed using the pellet press. As our program is remote, the press during operation will obey a set of input pressures, hold times, and more, with just one click. Illustrated above is the press with its shield on in case of a blowout. Our program is coded to measure the respective rate of oil input and magnitude of the oil pressure. In the case of a blowout, when the stainless steel gasket slips out of the anvils, the oil pressure would drastically change as the compressibility of air is remarkably different to that of steel. Luckily, our program will notify us immediately of sudden oil pressure changes and will immediately decompress the system in this event. Blowouts are more likely when there are large changes in volume, which could occur if a material that is being compressed has a phase change. Blowouts are also more likely to occur when we decompress. During decompression, we are pulling the anvils apart, which adds more volume to the sample chamber, enabling the gasket materials to slip. Finally, we can have blowouts generally at higher pressures, as we are forcing more and more material to crowd within a confined space. Otherwise, if we are synthesizing nanothreads, then we can sit back and wait 24 hours for the press to finish. The last step is to crack open our gasket and see what we made. We open our gaskets by cutting the steel manually. We often obtain between 1 to 3 milligrams of solid sample, which can vary in color, glassiness, and crystallinity depending on the pressure rates utilized, and obviously, the precursor material. Illustrated at the top is a sample of compressed pyridine, and at the bottom is a sample of compressed benzaldehyde.